Hello. Here, let's put this up a little bit. There we go. Hi, everybody. Welcome. It's August 6th right now. Whoa, we're August already. I'm really excited to do another Ask an Astronomer series. I'm going to introduce myself again. I'm Dr. Kevin Hainline. I'm an astronomer here at the University of Arizona. And I work on distant galaxies, and I also really like talking about space. And I've been doing this series to essentially talk about different topics in astronomy, kind of a light overview of the topic. And maybe in the future we'll come back to certain topics and go into them again in more detail. And as I give these talks, because I'm streaming live on YouTube, if you have comments or questions or something like that, you can just put them in the chat and ask. Oh, hello, Splendid Torch. Oh, excuse me, Cheetah Sweater. Oh gosh, Cheetah. I'm glad that you're watching this. This will be very different than what you just watched. But we're going to talk today about something that I think is pretty cool, which is imaging, astronomy images, and pretty pictures. Because I think astronomy is one of the great pretty picture fields in all of science. It's generally a thing where every year scientists have these big contest to see who can make the prettiest science picture, and there's lots of really good biology pictures and geology pictures of the Earth and stuff, and Earth sciences. But astronomy, man, like it's in a whole different realm, right? You get pictures of things that are so out, otherworldly by definition. And what I want to do is I want to kind of walk you through this idea of going from space, raw space, and light in space to the kind of pretty pictures that you see. Okay, and so we're going to start with the Omega Nebula here. So this is the Omega Nebula. So hopefully, if you've seen this before, I'm using Space Engine, this program Space Engine, and it allows me to kind of fly around here. So this is a nebula of gas, and if you go back, you can hear about nebula in one of my previous videos. But nebula is a big chunk of gas that is essentially a birthplace of stars. And this is this nebula here is inside of our own galaxy, but it's near one of the edges of our galaxy. It's you can see the galaxy as I warp around here. If we go like this, if we zoom out quite a bit, you can see where it is in relation to the whole galaxy. So let's zoom out. And so you can see that it's over near one of the edges of the galaxy, but similarly we are over near one of the edges of the galaxy. So let's go back to the Swan Nebula over here. And this, in Space Engine, this is their kind of artistic rendition of what it might look like, okay? And so you could think of this as a big pocket of gas. You're seeing kind of the brightest part of the gas. The gas extends farther, but it's only lit up by stars over in this region. And this star probably hundreds of stars worth of gas, all kind of in a big clump here. And as that gas gets in the clump, as we talked about in the star birth episode, it collapses down to make new baby stars, right? But when we look at this from the Earth, we have a very one particular view. But you can use really, and one of my friends, Jessica, she did this and for the Orion Nebula. But you can start to understand the three-dimensional structure of this, which is Space Engine has allowed for kind of 3D model of this nebula here. And you can see it kind of looks like it has a pocket in the middle. And that's, according to the Space Engine simulators, it's like where the stars are kind of glowing and lighting up all of the gas around it. Okay, so this nebula, very pretty. It looks very pink here, reddish, right? There's some dust in here, which is causing some of the reddening as well. But the question is, well, how do we take a picture of this? And and people ask me all the time, if you're floating in space, is this how this would actually look in space? You can see one of the baby stars right in here, right around the center. Would this actually be what it looks like in space? And that's kind of the point of today's talk. So. If we were to go to the Earth, so let's go home. I think if I do this, home. Why is it not working anymore? Earth. Go. Let's close this. If we go back to Earth, go there a lot faster. All right, so now we're here at the Earth, and we turn around. Milky Way kind of floating out in space, and let's look for the Swan Nebula. Press Enter, center on the Swan Nebula. Then we can use the kind of fancy telescope tools that we have here to zoom in, right? So if we just keep zooming, zoom, 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 zoom. Eventually you can start to see the Swan Nebula. So here it is. we were just looking at. Now, all these dots here are stars between us and the nebula generally, but there's other stars that are maybe on the other side, but most of the ones are between us. But this is essentially like what the Swan Nebula looks like from Earth according to Space Engine. And the thing is that we can change the, how well we can view this. And if you change the exposure so that it's a shorter exposure, you get less light. But like this, what you're seeing here, when we look at this, is we're seeing light from the stars, light hitting the gas and reflecting from the gas, or gas itself giving off light itself as it glows, coming to the Earth, right? And I'm going to talk about telescopes in a future talk, but a telescope essentially captures that light. We'll talk about all types of telescopes in a future one. But once you capture that light, what you'd want to do is you want to do what you do with a camera. So a modern camera, I could go get my digital camera, but it's fine. You know what a camera looks like. A modern camera, light goes into the lens, and it's focused down onto either film or a little chip. And so we're going to talk about the chip, which in a camera is called a CCD, and in your cell phone, like it's a similar thing. This chip essentially is sensitive to light, because what we want is we want the light that we see here to be. We have seen the Swan Nebula. I'm going to show you pictures of what the Swan Nebula actually looks like. This is the simulation in Space Engine is based on actual observations, and we'll go over. You'll see what Hubble looks. We'll have a whole section on the Swan Nebula, but just for right now, this is what it, like in Space Engine looks like. And I'm just, the light comes from it. It travels the distance. So you can see, it's 470 parsecs. So, probably a couple thousand or 1,000 light years away. It takes about 1,000, years for light to get across space. We take a telescope and then take all the light that we see and focus it down onto a little chip. What does that mean, focus the light down onto a chip? Well, if you imagine the light from different parts of this nebula, this big gas cloud, like light from over here and light from over here and light from over here, giving off signals, like you could imagine the light from over here is really bright. So there's brighter, more light coming from over here than from over here. And you'd want to measure that, right? So you could imagine the light coming from this region down here, like as little particles, and you're getting more of little particles. And so when you take that light and bounce it off of your telescope, as we'll talk about in the future, you want to have a chip where the light falls onto a specific part of the chip from that part of the nebula and gives more light to that part than other parts. So you're making an image by essentially saying, all right, I want to go through all of the parts of this nebula and kind of take a census of how bright are you? What type of light is passing off and bouncing or coming from there, and put it on that chip. So the chip will have essentially an image of the nebula or of whatever you're looking in space, but will be like a much smaller version for inside of your and your telescope is focusing all the light onto that chip, that small chip. And when I say chip, I think of it like a series of little pixels, and those pixels can count up how much light hits them. And then the neighbor can count up how much light is hitting them, and the neighbor can count up how much light is hitting them. And so we can convert that into an image, and the image will tell you in each pixel how much light hit that. And so if we do that for a whole image, we'll get a whole giant image of, like an image that we can look at our computer of what the nebula or whatever we're looking at is like. Okay, so like if I bring up the Swan Nebula, I think I can put the Swan Nebula, I think this right here. Here is an image of what the Swan Nebula, let's drop this down a couple, whoops, no, that's me going away. The game capture needs to go boom, 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 boom. All right, this is an image of part of the Swan Nebula. Okay, and so this is an actual Hubble image, color image of the Swan Nebula. And so you can see here, and if I, I don't know if you can see my mouse, I can probably, can I make a mouse go? But you can see here, I can point if I move the actual whole image here, like to where my finger is. You can see that there's like little ridges and stars and stuff. And essentially, if I drop this and turn this off again, like what you're seeing here is you're seeing a part, let's raise my velocity a lot faster. Not going fast at all. Oh, there we go. Yeah, you're seeing a part. Whoa, 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 whoa! I've gone to. Where's the Swan Nebula? Oh, I've lost my Swan Nebula. Sorry about that, everybody. What you're seeing here, that's why. It's because I'm actually currently not on, I'm currently sitting on the Earth. That's why it's like that. So we have not had the ability to do this with computer chips since the telescope was invented. Before computer chips, when telescopes were first invented, you just look through your eye and you take the light from a telescope and it would focus on your eye, and your eye's retina would act in the same way. Your retina has not chips or not pixels, but little cells that are sensitive to light, right? That's how your eye works. Your eye has a bunch of little rods and cones, which are little cells sensitive to light. But then we then used photographic plates, and photographic plates, you put some chemicals on it, and then little atoms of silver would act like pixels. But in the 80s and 90s, we started developing chips so that we could do this, these little chips. But if I go back to this image here, in fact, here let's make life a little easier. I can let's close that. Let's look up Omega Nebula, and let's turn on my browser because I should have the internet here. I should be able to see. So take the game capture and really drop that down. There we go. Aha. So this is an actual image of the Omega Nebula. That's a fancier version, but like this, where you can start to see that it's a much better simulation than the simulation that, like, you know, if I move this out of the way, like it's much better than the simulation that Space Engine is making. But if you were to zoom in and look at like individual parts, you'd see that it looks a little grainy and pixelated, and it looks grainy and pixelated because of exactly what I was saying, which is that the pixels here correspond to actual parts of the nebula, light from that part landing on the pixels and saying what's going on there. And then on top of that, there's other issues that we can talk about with telescopes. But what a telescope is doing generally is it's taking light from a space source, and it's let me shrink this window a little bit so that we can, because you don't need the. There we go. It's taking light from a space source and allowing it to be imaged onto a chip as a scientific image, okay? And so for modern astronomers, they don't do things with photographs, and they very rarely look at through telescopes with their eyes. They're going to be looking at astronomy in this way, through photographs like this, okay? But the photographs like this from the telescope don't look like this. When I get my photograph out from the telescope, it doesn't look red and beautiful like this. Okay, and so that's the point of this entire talk. But it starts with light coming in from space, going through our telescope, and being imaged onto a chip. Okay, when that light comes from space and lands on the chip, each pixel can generally, outside of some fancy stuff, generally just can tell, light hit me. Okay, light that is essentially light that the pixel is sensitive to, because it's not sensitive to all types of light, right? So what I'm saying is the pixel can't tell what color the light is that comes in there. It can't tell, this is red light, okay? It can't tell, this is whitish light. It can tell there's not a lot of light and a lot of light. So what we would need to do is figure out, how do we tell, why are these images in color? Why are these images in color if we can't, a pixel from these chips, which are called CCDs, why can they, if they can't tell what color something is, how do we know what color it is? Well, let's back up. So, with our digital cameras, I'm going to show you a picture I took with my phone, and it's a picture that is of a flower, like in a garden with some some plants behind it. But I'm going to show you what it looks like internal to the phone. Okay, are you ready for this? So if I look at this right here, let's make it out of the way a little bit. So this is what my phone sees. This picture that I took, like when it first takes the picture. Because my phone has a chip that's sensitive to 3 colors, red and green and blue. All these chips are right next to each other, and the light that comes in essentially goes to the red chip, the green chip, and the blue chip. When I say sensitive to that, I mean the chip itself could only see red light. And then another chip can only see green light. And another chip can only see blue light. Okay? So in this view, look at this flower here. Same flower in all 3. I can move myself so you can see that this is the same flower as this one. Is the same flower as this one. But something's going on in that the red chip filter shows it looking white, while the green filter shows it looking kind of darkish, and the blue filter also shows it looking darkish. So the question is, what color is the flower? Okay? If when the chip, you're seeing this and it's looking black and white. You're probably wondering, like, why does it look black and white? I thought you said couldn't detect color. Shouldn't it be red? Well, in this case, all the chip is saying is, I know where it's white, there's a lot of light of this color I can see. And where it's black, there's not a lot of light. So for instance, for this flower right here, the red chip is saying, I know there's a lot of light that I can see on this flower. But up here, this thing here, I can't see. There's not a lot of red light here. There's not a lot of red, there's ish red lights, but there's not a lot down and around here, right? Meanwhile, over here on the blue chip, this patch right here, there's a lot of blue light coming from this, right? Which is why it looks white, right? These little areas here have a bunch of red and green, not as much, but blue light as well, right? This area right here, you can see there's a lot of red light coming from it, but you can't see a lot of red light coming from here. So Cheetah just said it's red, and so this is a pretty cool thing. If we look at the actual image right here, you can see that, in fact, you were right. So here's the actual image, okay? And look, it's in fact very red. Up here you get some blue areas and you get green. And if you compare it, you can see, this is why over here the sky is blue. It's going over a lot of blue light because blue here is seen. And so what the three chips are doing is they're telling you, I know where red light is. I know where green light is. I know where blue light is, okay? And so this is how your chip just takes those three things and stacks them and combines them. And when you combine them, you get the center one. Okay, you get what this is, right? It happens so fast, you don't even pay attention. You click and take pictures. Your computer on your phone is just like, I can do this. Bam, 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 bam. It does some other fancy stuff, which we'll talk about in a little bit. But this is kind of one of the fundamental aspects of why astronomy images are colored, even though when we get the images, we get them black and white like this. Okay, so let me take a step back. Our eyes have cones which are sensitive to these colors as well, right? And rods which are sensitive to black and white, like changes of brightness as well. And they work together. Light, just on the whole, when it comes from sources in space or anything, it comes at a variety of different wavelengths or different colors, all kind of stacked together. So like for this flower above my head, what's going on is light is hitting the flower, and the flower is actually, the petals are absorbing most all of the light coming from the sun, except reflecting the red light. They're just taking all the red light. And the way you could think of this is like, imagine if I had a handful of crayons and I walked over to a kid who liked all colors but red, and he would take, or she would take, or they would take all the crayons and leave the red ones. And so now you have red crayons that are like, left over. And so the same thing with this. This flower, it's a red flower, it just really, really, really likes all wavelengths of light except red. Bounces the red off. And leaves, they actually absorb a lot of wavelengths and reflect off some specific wavelengths of green. The sky is doing something different. So if we go over here, the sky is doing something different. The reason the sky is blue is because as light from the sun comes into the atmosphere, blue light is scattered in a very specific way down to us, while the other light, passes through. And so you end up getting, that the blue light is scattered in a very specific way down to our eyes. It's not the same thing as like being as plants absorbing things. Like, my skin right now is absorbing most light. Melanin in the skin acts in a very specific way to absorb certain amounts of light and reflect certain light, which is why we have different skin tones. Like, that's literally it. Just as melanin in your skin. It has nothing to do with, anything except melanin in your skin, right? Like, I have tanner skin because I see more sun being in the south, right? Yes, so these videos are all in a playlist that so once this is done, it's all entirely saved. So, here's the question then. How do we get our pictures? How do we get our beautiful pictures of the Swan Nebula, right? Because telescopes, telescopes have to take pictures. Oh, I should say, if we go back to, I'll turn the internet back on. If I go to here, this is a kind of representation of what I was talking about when it comes to pixels. You could imagine that each one of these pixels, why is this behind me? Why am I, it's because I'm at the edge of my thing. Let me bring myself out. I like that I'm just dragging myself around here. Each one of these pixels here is like telling you how much light hit that pixel. And so you can see in this black pixel, not a lot of light hit that pixel. This white pixel, a lot of light hit that pixel. A medium amount of light hit that pixel. And so you could do this across a huge image and tell about the structures in the image because each individual pixel would add up to tell you how much light hit it. I think about it sometimes like light buckets, like light coming in, water, rain coming in and falling into different buckets. You could imagine putting buckets across an entire state and telling where's rain coming from more, right? But the question is, if you want to tell what color something is, like in a CCD, like in a cell camera, they have chips that are sensitive to specific types of light. But for a telescope, you want to build a camera that's sensitive to a bunch of types of light and then figure out how can you only capture light of specific wavelengths. And for that, you need a filter. And a filter is just like a fancy sunglasses. Here are my sunglasses. Put them on right now. You can see my ring light reflected in it. Sunglasses act to take light and reflect a lot of it away and also absorb a little bit of it, but mostly you let less pass through it than you would normally. So you can see that if I do this for you, I look darker here, although the camera is really trying to compensate for that by changing some of the settings. But I look darker than I would otherwise because less light is passing in through to the camera. This is a filter. And you could make a filter that would only let red light through or green light through. You've seen this because like red cellophane sometimes or red filters, like I don't know if I have a red filter in here. I should. I have something just as good. Here's one. I have a red filter. Here's a red filter. Look at this. What you're seeing here is not me through a red filter. You're just seeing the red light that I'm giving off coming through to the camera. A red filter, right? And so a red filter on this, if you were to put a red filter over your chip or at some point in your telescope, then the light that would pass through, only red light would get through. So when you had this exact type of image here, you'd essentially say, a lot of red light hit here, not a lot of red light hit here, right? Similar to the image of the flowers, right? If I turn the flowers back on, it's the exact same thing. You could use a filter that would say, I'm just going to put a filter on here and take a red image, and then I'll take a filter and put a green image, exactly like a 3D glasses. 3D glasses are a red filter and a blue filter, and then on the screen, they project a red image in, like a one eye image in red and one eye image in blue, and your red filter will not let the, like the blue light through. It'll only let the red light through, and the blue filter alter it. So your eyes see the images and then combine them in stereoscopic 3D, right? But these filters we use all the time, and telescopes use them. Here's a list, by the way, a non, full list. Oh, by the way, I'll talk about that in a second, of filters on the Hubble Space Telescope, right? So you can see the names here and the type and the filter wheel and notes about it and other bullshit about it that you don't really care about. But like essentially these are the names of the filters which tell you the wavelength. So it's not really red or green or blue. It's filters at specific wavelengths. I care about these filters, by the way, quite a bit, especially some of the filters that like are at longer wavelengths like A14 and these filters are important because when I look at things in space, sometimes I want to know what they look like exactly at a specific wavelength, and having filters like this really help. I have all of the filters that are on the James Webb Space Telescope, the most of the main filters that I work on, I have them memorized. I can tell you all about them because I think about them a lot because they are filters that will allow us to look at very specific wavelengths and colors of light in space. Okay. But what this means is when you look at astronomy images, you're not just looking at an image that's like, this is a red image. You're looking at an image taken through a filter. And there are filters that are reddish, or red, generally called red, or R-band filters, but they're very specific. And in this case, what I'm going to be talking about today are filters that are like these ones, because I'm going to be talking about Hubble's filters right now. But you should look, when you look at astronomy images, at like what filters are you looking at? Because generally they'll say what filters they'll be done, right? And so from that point, you can do what we were talking about earlier, and you can combine the filters, right? So this is kind of a diagram, diagnostic here, showing like how if you combine red and green and blue, it makes white light, right? Like you can decompose light into a red, a green, and a blue. And red and green together make yellow, red and blue together make a magenta, and red and green together make a cyan color. And if you've never done that, if you've ever taken a flashlight, pass it over a filter, red and green and blue filters, and combine them, it in fact does work like this. I worked at a science museum for years, and they had a whole light exhibit showing this, and I was always stunned. Kids don't seem to be that excited about it because they haven't gone through enough of their life to know that like this is kind of crazy. Kids are sometimes like this is why when you do magic for children, sometimes they're not impressed because like they haven't lived enough life to learn what is weird and what is not weird yet. Hey KJ, hello, Lancer. So anyway, welcome. So anyway, what I'm trying to say is, when we look through space, when we look at space, we have generally to take things through filters, and astronomers will do this. Will take things through filters. Sometimes they have CCDs on them, like digital cameras that they plug in their camera, and they don't put a filter on because the CCD has the chips to take the red, green, and blue. So I have put my Nikon, I have a camera that I plug into the back of, I plug into telescopes, and it already has a red, green, and blue. This is why when you take a picture with a Nikon or a Canon or anything, it takes a red, green, blue image already and combines them. It does all this stuff on its own. You don't have to put filters in. But for professional astronomy tools, like what you see on big telescopes, space telescopes as well, you don't, you can't, you can't just assume that it's going to do that. Generally, it doesn't. It has a detector on it that only is taking pictures of what light hits each pixel, right? And so your images are going to come out looking a lot like this, except bigger, and they're black and white, right? So at that point, you can take images in a bunch of different filters like this, from the ultraviolet to the infrared, and if you combine them all, I can put myself over here. If you combine them all, ultraviolet over here to the infrared, if you combine them all, you get a picture like what you see right here. Right, and what the thing that is cool about this is that why we care about putting filters is not just because it's pretty, but look at this, right? So if I go over here to ultraviolet, you see the ultraviolet image only has like purple up in this top region here, and like you see that there. But if you look over in infrared, you get like it's mostly bright in the very center, right? It's mostly bright in the very center, where my finger is. But like the very center doesn't come up at all here. And when we combine it, we see like the ultraviolet and the bluer wavelengths, they're really bright up here, but the center is really red. Well, that tells us about, I can actually, I can make my life like a million times easier by, whoops, let's not do that. By going like this and just pointing and getting out of the way, right? Make myself enormous. But what you're seeing here is that this is telling us about what is going on, what processes are going on. Young stars, baby stars, contain a lot more very blue, hot stars. And so this region that you're seeing here is a region of heavy star formation, right? Meanwhile, the center of the galaxy here doesn't have a lot of new stars. It's older stars, which is why you're seeing them more in the redder colors. And so the colors of things in space tell you a whole bunch about what's going on in them, which is why we care, which is why you build 4 quadrillion different filters into your space telescope. So let's shrink myself back down a bit. So let's get into, is this another? Yeah, here's another similar thing showing how you can take multiple images and combine them, to make your final astronomy image. But let's just do something, right, guys? Let's just do something. Let's turn the internet off here, and let's open up something pretty cool. This thing I'm gonna open up. Man, if astronomers find out that I'm showing the general public DS9, they're gonna like freak out. This is SAO image DS9. SAO image DS9 is not something that most astronomers show the public. It is a piece of software that I use to look at raw astronomy images. Right now it looks really boring. You can download it yourself. If I turn the internet back on, you can go and download it yourself. And maybe at the end of this you think, I really gotta have SAO image DS9. But like it's at, I just Googled SAO image DS9. And it's called DS9 because of Deep Space Nine, because astronomers are nerds. And it's, it comes in all kinds of flavors. It comes in Linux, Mac, Windows. You can download the source. It's an open source astronomy imaging tool. And I'm gonna show you how I use it. But there's other sources that also, can do a very similar thing. But what's neat is it can open up and view the raw astronomy images. And why would that matter? Well, because you have access to raw astronomy images. For instance, let's imagine you really want to take a look at a Hubble image. You might think, only astronomers can look at Hubble images. Wrong. Look at this. If I go back to the internet here, and I where's my, boom. This website, welcome to the Hubble Legacy Archive. This is hla.stsci.edu, right? I just Googled Hubble Legacy Archive and found it, right? You can just go back, Hubble Legacy Archive, right there. You can see the, click on it. See it says enter site here. Now you have this boring looking search engine, but what's something that you think is interesting that Hubble has looked at? Like the Swan Nebula, which we looked at earlier. If I Google search the Swan Nebula, boom, look at all this. You see all this? This looks, if you're not an astronomer, you might look at this and go, what is going on? Well, what you're seeing here is you're seeing a way to download actual astronomy images of the Swan Nebula. Swan Nebula tells you where it is in the sky, which is right ascension declination here. And you see how it has here. But also you can see the detector, which may not matter anything, but most importantly, you see it says spectral ELT right now, spectral element name. You see this F502N, F656N, F814W. These are filters. The ones that I showed you earlier, oops, I just closed the window, whatever. The ones that I showed you earlier, these are the filters. And at this point, you can actually go and download these, right? I can display, let's display the F502N image here, right? So I can click on this display. It's gonna open up another window that I don't think you guys can see. Yeah, here, let's add that window capture. There, yeah, boom. Oh, it's so big, and it's so. Is it in front of me right now? Yeah, let's drop this down. Boom, 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 boom. So this is the image that I just clicked on. And it's black and white as I was showing you earlier, and you can kind of zoom in here and look around it, and pan around it and stuff, and you can, click on various things in up here which don't matter to you. But like essentially, look, this is a raw Hubble. Like it's a slightly processed Hubble image, but it's a Hubble image you could just download yourself. How do you download it? So let's close this again. I'm gonna turn off that window capture. How do you download it? Well, you see where it has like a shopping cart that says fits? You just click that, right? So that same image, I click fits. It says added to cart. I go click on my cart up here, like I'm grocery shopping, and it says fetch HLA data, and you can just download it right there. But here's the thing. I've already done it for you. I've already downloaded it so that I can look at it. So let's go back. Let's turn off my internet here, my internet window, and let's turn back on the DS9 window. Oh, wait. Yeah. There. And let's play around with DS9. So let's open up. Let's do a new frame here. So the way the DS9 works is it works in frames. And you can always, again, go back and watch how I do all of this. This is not a tutorial for DS9. But now if I go to the pretty pictures in Swan Nebula, if I go and say, all right, so I've got F502, F656, F814. Let's do F502. And I click on it. Boom. Here we are. When you first look at it, it might not look like this. It might look like this. And you might go, where's my image? Okay. And here's the thing about astronomy images. Astronomy images are presented in a raw format. When you look at images with Photoshop, with other stuff, generally they do a pretty good job of making it so you can see the image. But this is a raw, it's called a FITS file. If you look up here where it says file, it says HST0657401 WIFPIC2 F502N.WIF.DRZ.FITS. This is a crazy thing. This is a .fits file, which is a raw image file with some extra bits that help me know where the telescope is pointing and what filters there. Like if I go and I go, oh, whoops. If I look at the display header here, if I click on that, can you guys see this? Is this something? I guess you can't see this. I'd have to add another window capture, don't I? So if I do this and I click on, is there another? Yeah, great. Hello, here. So this right here is the image header, which is the extra bit of information that came with this image, which is why it's a FITS file, and it's this raw FITS file. And you can see that it has a bunch of BS that you don't care about, that astronomers care about, right? In terms of how the image was taken and where it was pointed, like, how long they read out the telescope, and like what's the exposure time, right? That it was an 1800 second exposure, right? This is cool. This is telling you how long all this was done with Hubble. Like the Hubble Space Telescope, when was this taken, right? Let's go see if we can find out when it was taken. Date of observation, 05/30/1999. So, 21 years ago, right? They took this image, and it's available for you to look at, right? You can just go and look at this anytime you want and download it, right? But now you're saying, I want to look at it. I want to actually see the image. What's the image look like? Well, in DS9 image, we have to start. You can see there's all these like buttons here. You start by clicking on scale, and you can click Z-scale here. Z-scale is the one that essentially kind of tries to do a pretty good scaling. And now you've got the image, and you're saying, well, it looks a little bit, I can take and right-click on the image and drag around in the image, and look at this. I see more and different ways of scaling it, right? You see structure starting to come. If I middle click, and then I zoom in with my mouse wheel, you could see zooming in on this. And what I want to point out first is this is a Hubble image that's been combined from some other Hubble images and stacked, but it's a Hubble image in that you can see it's not perfect. And this is going to be confusing. You're like, what is this weird cross here? What are these little splotches? Well, the thing about an astronomy image is that astronomy images are taken on astronomy detectors, and the pixel, when you put something in space, and they're very expensive. You can't swap them out. If you get dead pixels, if you get pixels that are too hot or whatever, you just work around them. And so what you're seeing here is detector artifacts, pixels that are dead, pixels that, and like you're seeing edges of chips as well, edges of detectors. You're seeing, as this has been stacked from multiple ones, you're seeing parts over here where the stack doesn't have as much data, which is why it looks really pixelated over here. This right here is what astronomers look at. And this is a 502 image taken in 1999 of this Swan Nebula. And you can look at various parts right here and look. And the structure you're seeing here is real. These little splotches are not. But if you're going to try and make this into a pretty image, you've got to work around the fact that you have those by taking multiple ones and then looking at like stacking them such that those go away. And there's lots of clever ways of doing this that's outside of the realm of this discussion. But you could also do other scaling here. So if I do a log scaling, you can see that this part over here pops out really well. And this is just the way that you present this, right? So I'm not cheating. I'm not lying here. I'm just presenting it in a slightly different way. I could do a scale. I could do a power. And you can see that this really highlights some of the structure in the nebulosity here. Like, look at these tendrils, right? Again, this is the same image as this. It's just flipped around. So if I take this and let's shrink this down a little bit. Let's go back to here. Let's see if we can see the same structures in this right now. Can we see the same structures? Oh, sure we can. Sure we can. We can see the little knobbies that come off on the sides here. This is an upside down version of this image, right? So if I go and I take this version here, and let's take this and transform. Let's rotate 180 degrees. Boom. So now, and we have to, still do some, probably I bet you have to do some more flipping and stuff, but I think that here, yes, it's right there. That's exactly it. Here it is. Haha, watch this. Are you ready? Do you guys see? Do you see this is the same thing? What? Isn't that cool? So you're seeing the same thing. You're seeing the same structures, but it's slightly a little bit warped and twisted and stuff, but this is the same image, right? We've now lined it up perfectly. Right, you can see if I point right here, you can see this little knob is the same knob as you can see in, Isn't that cool? And we just downloaded it from the internet. This fancy astronomy image. Let's make it cooler. Let's show you something even cooler. So I'm gonna turn this off, and I'm gonna do something really wicked. So let's take this frame and let's delete this frame. And now, where I can click this under frame where it says RGB, and I can bring up, and you can't see this window. Let's move this window. Oh my gosh, can I not move this window? Yeah, there we go. Let's make this window be the window that if I do this window capture, I change this to RGB, boom, and then I turn that back on, this window is what just popped up, okay? And you can see it says red and green and blue, okay? So let's take the red and the green and the blue. Let's take the red one and let's open up an image as the red image. And you're saying, what do you mean as the red image? Well, if I go File, Open, I don't know if you can see this, and I open up this image as the red image, and then I go click green, and I open up another one of my images in a different filter as the green image, and then I go and open up, and I click on blue, and then I open up another image in a different filter as the blue image, and you're saying, what do you mean different filter? Well, what I literally did was, and if we go back to the Hubble Legacy Archive, so I bring up my internet again, we can see that I literally just said in my, let's look up Swan and Nebula again. I just said, okay, I've got 502, 656, and 814. This is the reddest because it's the longest wavelength one. I'll use this as red, and this 656 as green, and this 502 as blue, right? Pretty straightforward. So let's turn the internet off. And you're starting to see that there's some kind of bluish here. Now we get to play around. This is a tough game. I'm going to have to click between the two. But if I go back and I look at the blue and I scale it, Z-scale, and I like now drag with my right click, I can right click and drag like this. And let's do the same thing for green, and I right click and drag. You're seeing the different parts are kind of popping out. In the red, we right click and drag. And you're starting to see that the color is popping out, right? Maybe there's still too much blue, so let's drag the blue away a little bit, make it. This is a really, by the way, tough game to play, this thing that I'm doing now. Let's make the green come in. Not too much green. There we go. And now, can I lock the... I want to change the... If I do log, nope, power, back to power. You're starting to see now that if I go and bring the image again back, that the colors that you're seeing here are coming from the different filters showing different things. It's not perfect. I'm not doing a perfect job here, right? Like it's a little tough to go between this and this because you're saying like, wait, the red one is like so much. So if we go to red, we can really crank up that red. So let's go to red and can I do a square root? I want to like, no. Linear? There we go. Let's really get that red. We're starting to really see it a little bit better. And then the blue. It's hard because I'm using SAO image, which is not really the greatest for this. But like you're starting to see that we're able to add and co-add these things and actually make pretty astronomy images, okay? And this is what astronomers, if they want to make these pretty images, this is how they start, is they start by co-adding. But it's very complicated. I'm doing a pretty cruddy job right now. Like if I look at the scale parameters, which you can't see. There, and then let's do this. Can I do the same scale parameters? Do this. And if I do the red, do the scale parameters. I also crank that up by a lot. And then I, try. Let's really crank up the colors here. Whoops. Hello, green. I want it yellowish, and then the blue. It's really a tough game. It's really a tough game. But essentially, you can co-add this in DS9. And there's other programs that allow you to do this, right? And you're right. The people who do this professionally are artists, right? They are artists. Let's put Z-scale back on all three of them. There's a lot of red here. But it's a game that you play, and you can also do this in Photoshop. There are tools that allow you to take and import these things into Photoshop. These FITS files, there's a tool called FITS Liberator that Hubble website makes that allows you to import these into Photoshop. And at the end, you can then take these and look at these and import them, and then do a much better job than what you can do with DS9. But DS9 is not built for the artistry. It's mostly built as a way of like allowing astronomers to look at things. I hardly ever do RGB stuff. What I tend to do is I tend to look at this at individual images and change the stretch in individual images when they're in black and white, so that I can really look at stuff specifically. And so if you want to know about the Photoshop aspect of this, I don't know how updated it is, but if we go back to the internet here and we turn off DS9 for the moment, by DS9. Hello, DS9. I want you to... Are you still there? Why is DS9 acting like this? Oh, it's window capture 6. That's why. All right. If we go back to the internet here, DS9, are you... Did I lose DS9 forever? Uh-oh. Oh, it's because it's behind. Okay. Sorry, everyone. If I go back here, we can go like Astronomy Image Processing. And right here, it shows like how, no, that's not what I wanted. Fits Liberator, image processing introduction. This is the same thing I just was on. Fits Liberator. No, where's the thing? Where's the thing that I wanted? Photoshop. That's what I want. You can see this is a tutorial from astrobackyard.com that shows you how you can convert images, in the software in terms of the various things that this person uses, stacking images to do this, but like basic Photoshop image corrections for astrophotos, right? So here's another website from astropix.com showing you, like, if you click, this is like your original stack of images and then your final adjusted image, how you can go and take and stack images, and then also you can change and tweak the contrast and the settings to get final images, and they teach you, right? Like, look at how in Photoshop you can change the levels in RGB so that you can like add fill and like really make things pop. And so astronomy imaging is a thing where you take raw images, stack them based on different filters, red, a green, and a blue, and then at that point you tweak them in a Photoshop style thing by changing the levels and the curves. And there's incredible guides. Like, this is super easy for me. 5 incredibly useful astrophotography photo, tips that like show you about. Well, okay. I no thanks. I'm a Milky Way master, by definition. Like, you can see exactly how, these people use the eyedropper tools to try and fix and make things darker and change the gradients and stuff. Like, it's never a lie, right? And what's mostly important is it's never a lie. They're never like taking the images and adding and drawing stuff in, but the colors might not be what you would see with your eye, because a telescope can open up and take a longer exposure, which gets more light than our eye would be able to do. Our eye could not see this as well, right? And so this is what I try and show when I look at something like, so if I turn the internet, if I turn DS9 off right now, when I look at here, we can do the same thing by, like, you could imagine opening your eye more, like, hello. Like, this is opening your eye's shutter more, where you get more light, right? But your eye, generally in space, we might see something looking more like this, right? Where you're like, where did the nebula go? Like, why can I not see the nebula, right? Are we still, if I reset the zoom, are we still on the Earth? Okay. Right, you can kind of see the nebulas there, but it's not nearly as brilliant and beautiful. And like, it's because with a telescope, you can really open up your shutter. And notice also that the rest of the sky lights up as well, right? What was pretty dark, dark inky blackness of space, is now, there's actually quite a bit of light just from the stars in general, okay? And so this is the thing that astronomy telescopes and astronomy imaging is. It's taking light, putting it onto a chip through filters, taking those filtered images and stacking them using some tool like DS9 here. You can stack them with RGB. You could also stack them using Photoshop. Where's the page? I want to find that page. Astronomy Imaging Processing Fits Liberator Photoshop plugin. I want to find the, like, because Fits Liberator is the tool that, like, I had this, download the, like, it's the tool that there's a plugin, there's a Photoshop plugin, Fits Liberator. So if we go and notice there's a lot of videos as well, but like, this is the NASA ESA Photoshop Fits Liberator, and like, this is essentially the, all the bits that you would need and how to install it so that you can use Fits Liberator on, like, step-by-step guide to make your own images. Here's the page where it shows you, for this is, an older version of Photoshop, this is Photoshop Elements, but it shows you how you can use the tool to essentially assemble, and this is the same images, the Swan Nebula that I was using, where you can assemble the Fits images and slowly stack them. Notice that this is essentially showing you how to make these curves and make these pretty images. Now they're stacking and giving this, okay, this is a blue shade, so we're gonna give this a blue hue, kind of what I was doing. And look, once you get to here, like, you're pretty good, man. And then, like, just doing some fine tuning, you can actually just get, like, the image that is there. And I think maybe in a future one, I'll walk through this in my own version of Photoshop to show people how to use this, because it's something that, like, if you could make your own pretty astronomy images, like that's pretty wicked, right? That's pretty cool that you can make your own versions of these images just with Photoshop. Now, I don't know if there's other tools that allow you to do this that may be more up to date. What is the tool that, what's the stacking software? Deep Sky Stacker. So this is the tool that I think a lot of people use. It's a free astrophotography tool that allows you to, so if you look at screenshots, that allows you to go and stack images. You can stack them, and do all of this. It's kind of a more, like a amateur astronomy, professional amateur astronomy thing, where you can do a very similar thing where you see here with the RGB levels and doing the tweaking here. And so maybe what I'll do for a future one is I'll go and I'll download this and I'll walk you through one of these, because I think this is a introduction to this thing. But man, if you could do this yourself, this Hubble site, what do you think is cool? The Horsehead Nebula. Click on that. Boom. Here's Horsehead Nebula in WFC 3, right? These are images, and I actually I think I have Horsehead. Let's open up the Horsehead Nebula with DS9. While we're here, while we're doing it, we may as well. So let's delete this frame, and let's open. Oops, let's do a new frame, and let's open the Horsehead. So look at this. Here's the Horsehead Nebula. Right here, a zoom in on the Horsehead Nebula in the infrared. So you're seeing some through it, right? But now you could make an RGB image if you had two other ones from the same website and stack them. It's not hard to go download these things and look at this. If you think astronomy images are pretty, the artistry that's there is in fact artistry to tweak it just so that it's perfect and push and pull it. But you can go pretty far with publicly available free tools. And I urge you, if you like doing this, if you're a person who enjoys playing around with Photoshop and you want to make something, you can go and say, hey, you could make really cool images. All Hubble images are free to the public because they were publicly financed, because Hubble was a publicly financed image. And look at the Legacy Archive. You can go Google what you could do with this. But man, you know what's neat? If you want to make a cool Instagram post, go and download this picture right here, and there's a raw Hubble data, right? You can then go and futz with it in DS9, in SAO image. You can futz with it in Photoshop, providing you have the plugin to take the FITS file and put it in. And I don't know if FITS Liberator works, but other tools will. And if worst comes to absolute worst, what you can do is you can go and find an image like this, and you can just screen copy and then copy paste into Photoshop. If you can't, DS9 is free as well, and it can open up these, and you can tweak the contrast as much as you want, and then just copy paste. You can even save the image as a GIF or a JPEG or a PNG that you get out from this. You could just go save the image raw as an image and then just bring that into Photoshop and then stack that way, which pretty straightforward. But you can start with just what is exciting to you. And if you've ever looked at the Astronomy Picture of the Day website, so let's go back to the internet here. Let's look at APOD here. Have you ever been to the APOD? APOD's a really good homepage. APOD, the Astronomy Picture of the Day, is just has a new astronomy picture every day, and you can click and have it be really high resolution versions, and you can see image credit and copyright is Emmanuel Petrilli. They are an engineering student and astrophotographer, and look at these beautiful images, right? These are images they took themselves. Here's the Orion Nebula that they took themselves, right? Nebulosa di Orione, M42. And you can go and do this even without having a telescope yourself, by just using the telescope that is the Hubble Space Telescope that you have access to, right? So if you look at the archive, if we find Hubble, here, boom. Bright Planetary Nebula, NGC 7027 from Hubble. Let's go look at that, right? So you're saying, what a cool image. I wonder if I could do that. Well, let's go see if it's available. Search. Boom. 7027, you could say, okay, well, this right here is not, the target is not, but these 7027 ones right here, we can go and click on one of them, and actually, let's display this one right here. And let's open up that display, that window capture. There. And let's bring that up. So this is what I'm seeing here. I'll bring that up right here. Let's zoom in. I'm not seeing it initially. I wonder if it's in here, if it's in this image. Lighter. Huh, it doesn't look like it's in here. There's advanced contrast controls where you can change the saturation as well. But I'm not really seeing this in this 7027 combined image here for some reason. Weird. But I could look around more, but you could go and hypothetically, like, I wonder why detection image? Is this the detection image? Can I click that to display it? Will it change? Hello, here. I guess it's the same image, but I'm just not seeing it, unless that's something else that I'm totally not seeing. 7027 should be something that's pretty obvious in here, but maybe I'm not initially seeing it because I'm just pulling this out of my butt initially, right? But like if I go, like, let's look at 100 images here. Can I find another 7027? Can I display this one? Is this going to give another one? Oh, here's a color image. There we go. Here we go. All right, so this is a color stacked image here that's already been stacked, right? But if I look at 7027 in 656 from this same thing here, I'm almost out of time. Well, we're seeing, you know what it is we're looking at only one chunk of it. You can see that actually this down here, over down here, it's a really big thing. So this is a stack of a bunch of images. So the problem is that, like, there's a lot of images that went into making this, right? So if I click on this and display this one, hopefully we can find one where it's more close to the center. Oh, golly. Lighter, 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 lighter. Oh, wowie wow. Yeah, it's here. It's just really, really, really bright. And so the thing is that you'll have to watch out because sometimes things are really close and Hubble's got a really good zoom in. But the game is trying to find, and so like you could imagine in that website that I was just showing you, let's turn off this window because that's a gross, but you could imagine finding this image here, which is the one that I was looking at that like has 814 and 555. You could find that exact image, the 814 image, and hopefully this is it, a combined one here. Maybe not. It's hard to say. It's hard to find these things because I'm pulling it out of my butt. But you could like go through APOD until you find something that, like, if we go find another Hubble Porpoise Galaxy. Is this something we can look at? The Porpoise Galaxy? Oh man, that's really cool. Oh gosh, is that gonna be something we can look at? I gotta finish up here in a second, but Porpoise Galaxy, is that a thing that can? No, I'd have to find out what the Porpoise Galaxy is. Oh, it's an NGC 2936. That's what you wouldn't want to. You want to make sure that you call it by the most generic. Aha! So here's an NGC. Oh, come on, please be the galaxy. You can't see this yet. I'm going to only bring it up if it's actually the galaxy that you can see. Oh, baby! Oh, baby! Yeah. Here. Look at this. There it is. You can go download this image that was made to do that in those filters and make this image yourself. Maybe that's an exercise for the reader. Download these images, or maybe the next time we do this, we'll download these images and make something that's as cool as the porpoise image that you see here, right? It's the same thing. You're just seeing it, backwards, flip backwards. But look, raw Hubble image, beautiful Hubble image that you can stack and make yourself. Pretty cool, right? Okay, so it's 5:58, so I got to be finished up pretty soon. But hopefully this got you excited about doing this. Maybe next week I'll go through and take those raw images, we'll import it into Photoshop, we'll combine them together and make an image that's as pretty as this, which would be kind of fun. And I also want to talk about telescopes. We got a bunch of astronomy topics, but for right now, I just want to let you know, when you see these pretty pictures, remember you're seeing multiple images taken through different filters, stacked and stretched and pushed. This is not what you'd see with your naked eye, but it's something that you could imagine seeing if you had really big eyes or the ability to like stack images over time. And each individual color tells you a little bit about what's going on. Like in this case, this red right here is telling you about dust, and you're seeing stars being born over here. And you're seeing this galaxy right here has no baby stars in it, right? You're seeing the shapes here and there's a lot of information, and that's what astronomers are looking at. Pretty cool. I'm especially happy that I was able to find this thing here, because like this means you can download this, pretty straightforward, right? And like really just get these raw images yourself and play around with them, which is very, very cool. Because this image right here is in 606W. And there's also, if I go back to my Hubble image here and turn this off, my Hubble legacy site, you can see that there's 606W, 475W, 657, and 814. So just download these libfits files. You'd click on them all like this. You'd go, boom, 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 and click the fits and add them to the cart, right? Like a shopping cart. You could also, they have a color stacked image that they've stacked themselves, which uses 814, 606, and 475. So they don't use the 657N. That N means it's a narrow filter, so it's not going to be as bright in that band. And sure enough, if I go and stack those just using the tool here, look, this is just the stack of 814, 606, and 475 filters. Look at this. Pretty good. Just a stack. No pushing and tweaking, just a raw stack. Pretty good from Hubble. All right, everyone. Thank you for watching. I appreciate all the people who are watching for the first time. And if you have other questions, post them in the YouTube comments. If you want to know more, send me. You can also follow me on Twitter and Instagram here, where I post about things like this. And I hopefully next week or in 2 weeks I'll come back and we'll talk about actually creating an image like this with Photoshop, which would be pretty fun. But you guys are wonderful. I appreciate all you watching, and have a nice rest of your day. See you. Bye. Bye, KJ. Bye, Lancer. Bye, Cheetah. Bye, anyone else watching. You're all wonderful. Bye.